So we're in week 5, the second week, 4 and 5, of talking about fluid dynamics, Bernoulli, in other words, and we've talked about that both along a streamline, which is primarily the way we'll use it, and you could use it to solve this problem, and perhaps we will. So one question you might ask yourself is, what kind of velocity you need to come out of these jets to be able to lift a human, to do all these wonderful things. I think these are $50,000 or something, the so-called jet lift. Quite an interesting idea. And I have some later videos where you see a whole phalanx of 10 of these things doing acrobatics kind of in unison, like synchronized swimming, but also diving below the water. Of course, there's nothing to stop you going underwater with these jets, and they do it. And so, yeah, the jet, so-called jet lev. And so you see it's a package at the back which has a pump in it. That pump serves this umbilical cord, this yellow tube, which gives you pressurized water, and then the pressurized water comes out with the jets, which I guess you change the attitude of the jets, and you change the force of the jets with this controller to be able to lift you higher or lower and allow you to get some forward motion by inclining the jets at an angle behind you. So quite an interesting way to be able to travel. And so that's something certainly that you have the tools in your arsenal now to be able to deal with. What else have we got? A couple of other things. Don't know what that was for. This I thought was interesting. I guess it's not a movie, but it's just a figure. The Flying Scotsman. Of course, the Flying Scotsman used to be the name of a steam-powered train in the running from probably Edinburgh to London, or perhaps Glasgow, probably Edinburgh to London, and had a land speed record at some time, I'm sure. But this is a Scottish guy. You can see he's lying prone with his butt up in the air and his feet at the end here, and setting a land speed record by pedaling fast. And of course the cockpit that he's in, I guess he has a little windshield out here, is especially designed to be aerodynamic. And of course you can do the same calculation with what you have now with the Bernoulli equation to be able to say something about, for instance, what kind of power he has to expend to be able to go at 56.62 miles an hour to make this world speed record. And the final thing, a bit more sobering, is we've talked about this before as well, is the Air France Flight 447. This is the flight that left Rio de Janeiro for Paris, and unfortunately for the greeters at Paris never arrived. And this was it traveled through a storm. The storm was such that the air temperatures were cold enough that it froze the Pitot tube. The Pitot tube is the tube that, despite GPS and all those wonderful things, is still used on planes today to get airspeed, an actual real magnitude of airspeed, from looking at the killing of velocity, stagnation at the front of this little right-angled tube, which sits on the cockpit below the pilot's window as you get onto the planes in State College, if you ever fly out of State College, and all other planes. It's just that you see it when you walk in from the runway instead of an enclosed jetway. And it froze, and so no longer could air get into it and be stagnated, and so it didn't have a reliable reading on airspeed, and so the plane dove and climbed and dove and climbed and ultimately dove into the ocean straight away. And sobering thought about all of these things. So anyway, so that's kind of what we will talk about today. In terms of order of business, we're in week 5. Week 6 is test week, midterm week. So something went out over the weekend. So you know that for this class in the syllabus, two things to look at that might be useful. So in the syllabus, we've got it all laid out so that the reds are in Pollock, so you've got all day to do them. I guess we'll have class those days unless you really vote that you don't want them and rather get extra credit. I'm fine that. And clearly on the Friday when it's in the class period, somewhere, could be here, could be in your home, same rules, ground rules, no communication, then we can't have class obviously on Friday for sure. But that's next week, not today. So the email that came out, I guess it was it midnight Saturday, I think, so you saw that. The format and review materials for the test are exactly as given in this video. You can look at the historic ones for over many years and compare them if you like, if you don't trust me, with the exam scripts from those years, and I think you'll see that you basically get every equation that you need. And so for this year in the testing center, this exam sheet or this equation sheet will be appended at the end of the exam script, just like it is in the practice exam. So you can't take a test in, and the reason, you'll have this with you, but you can't bring it you can bring a calculator and a pencil, and you'll get scratch paper for the 2 days that we spend there. We can't get the testing center on Friday. We could get it on Thursday, but instead of taking it on Thursday, I decided just to stay true to the Monday, Wednesday, Friday thing. We've always done this class online in your home, but last year I think there was a bit more interaction amongst people going on than I really wanted to. It was fine during COVID when everyone was separated in their parents' basements somewhere around the country, but now I think that's not so much the case. And so that's the reason for changing it slightly. So you can review the video and see what's going on. It should include all the equations that you need and the rationale. It's really an abridged version of what we've talked about in class, so you can know what you go back to. You see at the top of this numbers 1, 2, and 3 for the Monday, Wednesday, and Friday. Gives you a pretty good clue as to what's going on. And I'd say again, the biggest arbiter of doing well in this class, I would say, is by downloading the exams early on and having a look at them. And so if you see what the materials are on these individual questions, then I think you should hone in on stuff. I'm getting less and less creative, so I endeavor to have a unique exam every year for the 15 years I've been teaching this class, but I'm kind of getting out of ideas. So how different can they be? Certainly more than 3 or 4 years ago, pre-COVID, they'd have been longer tests because they were tests in person on a Wednesday night from 8 until 10, all 3 questions, and people stayed till midnight if they wished to, and so they're a bit more involved. But these are specifically made for these 30-minute sound bites in the testing center. So, yeah.
The Thursday review session, is that going to be on Canvas? Like on the syllabus, there's the blue circle.
That's when this will be posted.
Oh, okay.
That's all. So there is no review session. So, but, yeah.
Wednesday exam, do we have to set up a date, or do we just walk in the process?
No, I think they contact you. It's the first time I've done this, so I shall find that out for you.
This morning, you should get the email. All right.
Yeah, you get an email and pick your slot.
Yeah, I think that's what it is. So, and it's all day available. So it'll be new for you, and it'll be new for me as well. So I'll be interested to see what the commentary is on that. So yeah, so the review session is recorded and uploaded by the Thursday to give you enough time to get stuff together, but actually it was uploaded a week Saturday, so it's fine. I'm super efficient anyway, so have a look at that, and so don't get too jazzed about it. It is what it is. So you've seen all this stuff in class, and it is, I do endeavor, as is fair of course, to have a test which, to the extent possible, they're not follow-on questions, so that if you get question 1 wrong, certainly you get question 2, 3, 4, and 5 wrong. It's set up to be it's kind of as independent as it can be, but of course it can't be completely independent. So try and make it a real evaluation of what you really know about this. And so it's the same as the practice exam exactly, so have a look at that online on Canvas and work your way through that. You can take it as many times as you want. You can see how it works. All the questions, some are multiple choice, but most are numerical, and they have a plus or minus 10% on them, which is fine. So which is fair, I think. Anything else? Never fun to talk about tests, but it is what it is. So that's that. Anything else? Anything else before we get? So anyway, you can ask questions as needed. What did you do last week? Well, let's run through at 30 speed what you did last.
And so,
So 4-1 should have been the oxymoronic question of accelerating static fluids, both linearly and rotationally. One of the questions is a linear acceleration question. And so we used the equations we'd already developed to look at pressure changes within buckets. And if you accelerate a bucket across the front of the room, the level of it raises, which is why we have those train carriages which were flared at the front, so that when the train takes off and accelerates, it doesn't pop the cap because the level rises. And you know that if you're accelerating horizontally, it would stack up towards the back of the bulldozer you're pushing it. If you're accelerating vertically, you get an extra component of gravity. If you're coming down an elevator shaft at gravitational acceleration, the water will be weightless, so the variation in pressure with depth will be zero. You'd have seen those when we're talking about them. And we also talked about taking a bucket and swinging it around your head. If it's in a cylinder, then it gets pushed out by centripetal force to the sides and raises itself, so that instead of an analog for pushing it across the room and having a linearly raised surface, in a swirling container is that it has a curved surface up towards the outer boundaries. And there is no rotational acceleration question on the test. So that was 4-1, as I say, oxymoronically labeled acceleration in static fluids.
So for the benefit of this, you can check in the previous year's tests and previous year's reviews that
That's
most of
exactly.
the only.
So I guess we were right on schedule today. That was last year's one. And then we started talking about Bernoulli. And so Bernoulli comes in two forms after recapping on the previous stuff. And described what Bernoulli is. You've probably seen Bernoulli. You write pressure, elevation, and velocity heads at one point. Downstream on a streamline, you can equate those three components to the same magnitude downstream. And if you link those two terms, if you have 5 knowns and 1 unknown, you can solve for the 1 unknown in that expression. We probably showed that it comes out of F equals ma, which was the same equation that we used right off, maybe on the 2-1, the first class in the second week. And we can use it to say something about how pressures change along streamlines. Again, we get this interplay between pressure head, the elevation, the pressure at that point, and the velocity of that fluid at that point. And those all sum up to a constant along a particular streamline. And you can illustrate that with this syringe. And I think we probably did a question online about a jet at San Francisco International blowing a truck off the taxiway, and did a reasonable approximation for exactly what that truck should weigh, something like 1,500 kilograms, which is about right, I think, for a truck. Of course, it was a staged demonstration, but it just allows us to be able to, using Bernoulli, from the velocity coming out of the jet engine to the pressure at the stagnation point on the truck. Those are the two variables we want. If we know the velocity coming out of the jet engine that's killed when it hits the truck, we get the pressure that develops, and we can use that pressure to calculate the force, rotating it over. So that was that. And the third one from last week, again, don't want to hear Donald Duck. Jet levs in terms of a thrust. Can't remember it. Jesse James, it's not his right name, going off Niagara Falls. They never found him. They found his kayak, but they never found him. People do go across the falls in barrels and survive, but and I think people have gone across the falls in kayaks and survived, but I don't know. And we certainly saw some people doing free falls off waterfalls into deep plunge pools in some of our videos in getting going. Yeah, I think this is a recap of the same truck deal, right? To be able to explain what pressures on a face are. Of course, it's a gas that's on the truck, and so the pressure distribution with depth is kind of linear, but it's almost flat, so it's just basically a straight pressure. And then we talked about pressures normal to streamlines. So as you go along a streamline, the velocity along the streamline is the maximum velocity because that defines a streamline. If you go orthogonal to the streamline, then there is no flow in that direction because you're going across the directions of flow. But you can look at it just as if you're twirling a bucket around your head, and the bottom line is that you get a different relationship for Bernoulli that allows you to look at the pressure distribution as you go across the streamline. And the takeaway point, I suppose, is if you're driving your car and you go into a dip, you get pressed into your seat, and therefore you'd expect that if you're carrying a coffee mug, then the pressure distribution in the coffee mug, instead of just being this linear distribution, it's larger than that linear distribution. So the pressure is larger than it would be. If you're going across the crest of a hill, then it's the opposite. You have gravity, but it really subtracts that gravity. And so the distribution of the pressure within your coffee cup is actually less than it would be if it was just a static fluid. And that's the kind of take home. And it's kind of a complicated way to get there, but that's really the message for going across a streamline. I don't think there's an across streamline question on the test. I'm pretty sure. Yeah, you can confirm from what we talked about. And then I guess we did some examples with using Bernoulli to be able to calculate the one unknown parameter if we know all other five by writing it at 2 points. Right at the top of the fall where you're happily going towards the horizon line, not realizing what's ahead, and then you can calculate what your impact velocity is just before you impact. And of course, just after you impact, point number 3 on this is you can calculate what pressures are on you as your velocity goes from a big number to 0 number, and you kill all that momentum. So really what we're doing is F equals ma. F equals ma, acceleration is dv dt. So it's F equals mass times rate of change of velocity. And so you can write m times v as a rate of change of momentum. That's really what Newton's law is, Newton's second law is. And so that's kind of where we are. And so today, after I've talked for so long, we'll carry on and we'll spend the rest of the week on Bernoulli and talk about that. And you have the 2 components there. By far the most useful Bernoulli equation is along a streamline version, which is what we have here. And I perhaps don't need to recap, but you understand that you have ostensibly an upstream portion, a downstream portion along a streamline. So I guess we often use this kind of picture with fluid going along it. Anywhere along this streamline, you can write it at a point. And this would be upstream and this would be downstream. For what we've talked about so far, it doesn't matter. They could be reversed because there's no losses in the system. We know that for Bernoulli, it's ostensibly for as inviscid fluid, no viscosity, although it works for fluids that clearly have viscosity. It's for an incompressible fluid where the modulus goes to infinity, like water. But we also use it for air, works perfectly well for air. It's also for irrotational flows, so you can't have eddies in it. And I forget what the other condition is, but it doesn't matter. We can use it in lots of places where the conditions only nominally apply. So you write upstream, you write it downstream. We have components in there which represent energy that you have to put in the system. So for instance, if you're looking at flow along a pipe between upstream and downstream, then you can write it between downstream and upstream. This would have to be the direction of flow. And you can write it for a pump. And a pump head goes in there, the head of the pump. These are in units of length by definition. Oranges to oranges, apples to apples. So this is length, so these have to be units of length. This has to be units of length. This is equal to the power joules per second, Newton meters per second, joules rather. Watts is a joule per second, Newton meters per second. And it's as a function of volumetric flow rate times density times gravity. So if HP is positive, it's a pump, and you're putting energy into the system. If it's negative, it's a turbine, and you're taking energy out of the system. So that's the sign convention. And we haven't talked about it yet, but we'll talk about losses. And these are for the fact that when you flow down a pipe, the water that flows down the pipe has a drag on the side of the pipe, and you're losing energy. You lose it as heat. And so if you want to accommodate that, which is really if you dimension a pump to pump out water out of the ground, you're dimensioning it to provide enough head, because these also have to be units of length, that give you enough pump head to be able to overcome the resistance to flow within the pipes. So we don't need to talk about that. We talked about this going across streamlines. It's not on your test, so let's not worry about it. It's not on this test anyway, right? Because it's outside the bounds of this test. So that's Bernoulli equation. By far, we'll use a long streamline version, and of course, perpendicular streamline in this normal direction versus the streamline direction. This is the maximum flow velocity here. The flow velocity in this direction is 0 because it's going across the flow. So when we use in this normal to streamline version here, this is the streamline velocity. It's not the velocity normal to the streamline, because the velocity normal to the streamline is 0 for what we've talked about here. So, good? Pedantic enough for you to go through everything? So we're going to talk about free jets, and we'll talk about continuity. So that's where we are. Pitot tube. Why don't I just do it impromptu, just for a change? Well, did you see a Pitot tube? Well, here's a Pitot tube. This is the right angle thing that goes on the side of the plane. This is pointing forwards. This is attached to the fuselage, and it has a bunch of ports in it. It has a port that gives a open tube with a pressure transducer here that measures the pressure that results at this point. And it has a couple of other ports that measure the pressure just due to the fluid that's going past it. So the fluid comes down here. It stagnates at this point here, so the velocity is 0. But the velocity that occurs here maintains the velocity that's coming. The other parameter that we need to have is that it's steady state. That's the fourth one. So in other words, if I'm looking at this wing, the velocity at this point at time 0 has to equal the velocity at this point 10 minutes later. So that means that you have to be attached to the reference frame of the plane. You have to be looking out of your passenger seat onto the plane, not sitting next to the runway as the plane takes off, because that's changing. So you have to choose your reference frame so that it's steady state. So clearly the flow that goes past this, if you take a picture now, take a picture 10 minutes, the form of the flow around the wing is exactly the same. So it satisfies this. So all by way of saying, if you take this geometry here, you're attaching yourself to the plane, so that the flow that comes past this is relative to you. So what we could do is I could write the velocity at this point 1, and I could write it at 2. So I'm not going to follow this, but I'm going to use this figure. So Bernoulli says elevation C1 plus pressure P1 over the unit weight of the fluid plus V1 squared over 2G has to equal the elevation at some other point. You'll be tired of writing this equation by the time we're done. So I'm writing it at this point here. So this is, so if you like, the flow is, what are the conditions here? This is velocity V1, it's pressure P1, and it's elevation Z1. This is velocity V2, pressure P2, and elevation Z2. And so what are these magnitudes going to be? Well, this is a velocity that we'd like to know. We know that this velocity here is 0. It's coming along, it's hitting the blunt end of this tube, so it's killed all its momentum. And so this magnitude is 0. The pressure we don't know. The atmospheric pressure would be the pressure at this point, which is whatever the pressure is at that elevation. And of course, you could measure that pressure at this point 1 here as well, because you could have a pressure transducer measuring it. And let's assume that the elevations of these 2 points are the same. So they cancel out. So we get rid of, if I use my pen here, we get rid of this, we get rid of this. We would like to know exactly what this velocity here is. And so we can rearrange this term into this. We know that this velocity is equal to 0. And so if we rearrange it, we're going to want to rearrange it in terms of velocity 1. So velocity 1 is static in reality, but we're taking a different frame of reference that we're assuming that the pitot tube is static and the wind is flowing against it. So this will be the true velocity that we want. So this will give us V1 squared over 2g is equal to P2 minus P1 over unit weight. So I'm just moving this to the other side. Is that all we've got left? I think that is, right? Because this is 0. And so we can solve that for, and I'll just write it out. V1 is equal to 2g P2 minus P1 divided by unit weight. And if it's a V squared, we're square rooting it. So that's all. So I'm just rewriting this. Obviously, this magnitude here is rho g. Rho is the density of air, and so you get rid of the g's and you just have the rho on the bottom. But that's it. So in other words, all the Pitot tube is doing, it's named for a guy called Pitot, a French engineer, scientist, I guess. And all it does is it's killing the velocity at this point. It's converting that energy that it has from kinetic energy into a pressure. It's measuring that pressure with a pressure transducer. It's comparing the pressure at point 2 and point 1 to get a velocity, and it comes out of this. And so I guess what happened in flight, was it 447, was that ice formed across here or on here, so it couldn't measure the pressures. And the solution for that was to have a heater element in the Pitot tube that stops ice forming. Very simple solution, but unfortunately it took 300 people not reaching Paris to do that. Often the way that lots of things do. The other tragic thing in the news, of course, this week is Libya, right? The dams, which are not really an engineering misstep. It was a bad maintenance of these dams in eastern Libya that collapsed and maybe killed 20,000 people. So tragic. Pitot tubes, this is just talking about what the magnitudes of the pressures might be if you're doing this. You can imagine in this case, if you have a pressure going across the top of here, then it might saltate as it hits here. So pressure builds up. You kill the velocity at this point. If you kill the velocity, you'll increase the pressure, and therefore you might have a higher pressure measured at that point. Here, if you think about it, this is a bit like the car going over at the top of the hill with your coffee cup. It's going over a bump, and so the pressure that you'd expect to see here would be less than the magnitude due to just the self-weight of it. And if you're going across a flat surface, then hopefully you're just measuring the pressure at this point, just as you're attempting to do at this point on the Pitot tube. So, throwaway comments. I guess you could have Pitot tubes that are angled, so that you could imagine, apparently they do have Pitot tubes that are angled. So if this is the element that's going into the wind, So this is moving from to your left. I guess that's right. It's moving to your left, or if the wind is coming from the left to the right, then you'd expect that at point 2, because you're killing it straight on, you'd measure the highest pressure change at this point and less pressure changes above and below. And so you could, if they're symmetric above and below, perhaps you'd think that 2 is pointing right into the wind. If the wind was coming at an angle, then from the lack of symmetry of these 3 pressures, you might assume that you're at some angle as well. Okay, so that's the first thing. So we're talking about pitot tubes. The other thing that we can do, we can invoke something called continuity. And so if you want to solve Bernoulli's equation, you have 6 items, so you need only to have 1 equation and 1 unknown. But if you have 2 unknowns, you can constrain this, and the easiest way you can constrain it is by looking at flow within a stream tube. So we've talked about flow in a streamline. So if you had 2 streamlines which are adjacent to each other, and you have flow at the upstream location, which is V1, and the cross-sectional area here is A1. And if we have V2 and the cross-sectional area A2, and we have a fluid flowing which is of density rho, then along this bottom streamline, you know that no fluids can go across it because every particle of fluid is following it. You know this adjacent streamline right above it, so it's the same as looking at the streamlines that would go across the top of a wing. You know, the next streamline would be above it and kind of parallel to it and going downstream. So you know that for that top streamline also, no fluid is going across it. Particle that starts off here has to go here and then here. And so no fluid goes across this boundary. So the volume rate that goes in here, so Q1 would equal the velocity 1 times the area 1 times the density. I guess Q is a volume rate. So this Q1 would be VA, which is in units of meters per second and meters squared. Area has to be into the page as well, right? So this is meters cubed per second is the volume. Multiplied by density is kilograms per meter cubed. So this units are kilograms per second by definition. The downstream flow rate would be rho Q2, which would be equal to density times volume, velocity 2 times area 2. And so what you can do is you can equate this with this. And all it's saying is that whatever comes in here has to come out here, and it has to come out at the same rate unless you're accumulating fluid within this, between these streamlines. You can't accumulate fluid in those streamlines because we've said the fluid can't compress, and therefore the streamlines would have to grow to a bigger volume to be able to accommodate it. And so this requirement that volume in equals volume out is that rho V1 A1 has to equal rho V2 A2. And typically the densities will be the same, so we don't care about that. And so the product of the velocity times the upstream area is equal to the downstream velocity times the downstream area between the streamlines. So this gives us a second equation, and it includes only velocities that we have in the Bernoulli equation, V1 and V2 squared in that case. So now we have the ability to have 2 equations with 6 unknowns, so we only need we can have 2 unknowns that we want to determine, and we can use this to constrain it. So this is the continuity equation that we'll use. So this is basically it here. Don't know we'll use it today, but we may do. So this is it, simply spoken. So it allows us to be able to, instead of having only 5 knowns, we only need 4 knowns. So that's that. And then the other thing that we're going to do was free jets. And so free jets, again, is a simple nothing simple, but a standard result that we get to be able to define the behavior. So people who do best in this class are those who can visualize how to put these problems together, because I think that's the kind of the art of it. So we have a tank here. The tank has a jet, a free jet that's coming out of the bottom. we happen to show that it's coming out vertically. It could be coming out horizontally. It doesn't matter. And so we'd want to know what the velocity of that free jet is. And so we can do it exactly the same as we've done here. Let's write Bernoulli's equation. I guess you've got it here, but let's do it anyway. P1 over, I like to write it in terms of lengths. I always write in terms of lengths. Plus, well, I guess it's written differently. V1 squared over 2g plus Z1 is equal to P2 over unit weight plus V2 squared over 2g plus Z2. So in these, what do we know? I guess we know that this would be V1. We can use the big tank approximation. If the tank is huge, then by definition, the rate at which this surface is moving downwards compared to the velocity it's coming out of here is small, because it has a big surface area to buffer all that flow volume that's coming out of it. So, and of course you can show it from this, right? If the velocity at 2 is large and the area is small, and this is a very big area here, then the velocity here approaches 0. So I guess that's why we did continuity, to be able to make that rationale. What's the pressure at this point? It's atmospheric. So we're taking gauge as 0, then the pressure would be atmospheric, and that's 0. And the elevation, Z1, well, we've got that. So relative to the datum, Z1 would be equal to equals H. Down at the bottom. All right, let's do the same. V2, what is it? That's a big number. That's what we want to get. So we want to write our equation in terms of that. Pressure. We said that pressure always acts uniformly at a point. So we know that at this point here, if we write 2 here, the pressure acting on the side has to be atmospheric. And therefore, if the pressure acting on the side is atmospheric, it's probably a pretty good approximation that within the stream of the liquid, it's also 0. So we can write that as being 0. And we need to know whatever the elevation is. And if that happens to be at the datum, then that is equal to 0. So this is 0. This is 0. Z2, just by choosing the datum there. The datum we can place anywhere, but we're going to take it upwards at that location. We take our sign convention to be positive upwards. So Z is positive upwards. And so we have this. I guess this is H. And this is 0. And so if we rearrange this, we get Z1 is equal to V squared 2 over 2G. This is the term that we want to get. So we just rearrange that. So 2G times Z1 equals V2 squared. I'm going to square root both sides. And if I do that, hopefully you can see that. That's your standard result down here. Well, and I didn't change. This is H, and so this is the standard result. So that's the equation of a free jet. It basically says that if you start off at this point here and have it coming out of the bottom, it's coming out at this velocity, which is square root 2g, whatever the height is. It turns out that also you could have this going down here. And you could measure it at 0.5. And if you measured it at 0.5, I guess it probably says this further down, then the velocity would be equal to 2gh plus h by inference, right? So 0.5 is a unit length h plus h below, and therefore this would be the velocity here. So clearly, h plus h is bigger than just h, and so it's doing what you expect it to. It's speeding up as it goes down. And so if it's speeding up as it goes down, also as a function of this continuity equation, this is we'll call this conservation of mass, or continuity equation, both apply to it. This is saying that mass is conserved as you go downstream. In other words, it's not evaporating anywhere. So from this, you could also say that relative to this point here, the same volumetric flow rate is coming across the cross-section of flow here as is coming across here. If it's coming across slower at this point than it is at this point, then it has to be speeding up. It has to be going faster. So it makes perfect sense that it's speeding up. And of course, if you wanted to convince yourself of that, then we could go back and we could write F equals ma, which we've done, which is what we can also write as mass times rate of change of velocity with time. Or as a substantial derivative, I guess we can also write it as mass times dv dt. And the reason for writing it that way is that what I could do is I could write this by multiplied by 1, as we've done before. And you'll remember that what we call this is the convective acceleration. Change in z with t is how quick, as you go from this location to this location in a small time, this is the velocity in the z direction. So this convective acceleration is the velocity z multiplied by dvz dz, right? This is the acceleration in the z direction, but not written in terms of, you see that we've factored time out of it. You could calculate your acceleration by measuring how quickly when you're at this point downstream in the car, and the time it takes between those 2 points. That's dv, that's dx dt, which is an acceleration, a velocity change, which you can get acceleration from. Or you can get the convective acceleration. So this is saying that at this point here, you have a velocity v5, and you know exactly what that velocity is. This is equal to, velocity is equal to 2gz, where z would just be equal to the distance from where you started off at zero velocity. And you could differentiate this this equation to get dv dz, quite a simple differentiation. If you put those together, what do you think the acceleration would be? It'd turn out to be that. You already got a g in there. And it makes perfect sense. This stuff's coming out of the bottom of this tub. It's just falling down. As soon as it comes out, it's just free falling in air. You could cut it off at this point and imagine the drop coming out. It's just falling to the ground and accelerating due to gravity. And so acceleration we can define either as dv dt, as in here, attached to the particle, or we can calculate what it is at a point that it's static. And at that point, which is static, it has a velocity, and it has a rate of change of that velocity, and the product of those two values gives you the same as you were that bead of water falling down and calculating your rate of change of velocity yourself as you're falling down. They're exactly equivalent to each other. I've belabored that point, and I shouldn't have done. What else? Don't need to talk about that. Magic. I was going to do something. I was going to do a jet lab. Maybe I'll do it next time. Yeah, it's good to get a slow start to things. So, we've done a couple of important things today. We've talked about Bernoulli, just to mention that we should do it between upstream and downstream. We don't really need to do that yet unless we're using these things like the pump head and losses, which we're not doing yet. We're just using Bernoulli without this term in it. It's equivalent to each other at these two locations, which means there are no energy losses within the system. And there are no energy losses because we're assuming that it's inviscid. So the viscosity is 0, so there's no frictional losses along the pipe as you go, and so there's no loss which is lost as heat in the system. And when we write it, bless you, we have 6 unknowns. So if we have only one equation, we can only solve for one parameter. We have to know 5 of the other parameters. And if we don't know another one, then what we can do is we can use that to link the two velocities in the equation by writing velocity 1 times the cross-sectional area of flow at point 1 is equal to the velocity 2 multiplied by the cross-sectional area of flow at that location. And that allows us to basically combine these two terms into one. That's kind of how it gets rid of. So then we have Bernoulli's equation written through this manipulation. We only need 4 known parameters to get 2 unknowns. And that's by using this so-called continuity equation or conservation of mass equation that we have here. And I suppose I didn't really think it before this morning, but of course that's the reason why we are able to make this assumption that the velocity at this top surface is 0. If you ever see an exam question, a big tank, that's code for the fact that the tank is big enough that this fluid is not moving because this cross-sectional area of flow here, which is on a streamline, perpendicular to a streamline, this is a streamline that goes through here, this is perpendicular to a streamline, so this area across here would be A1. This area across here would be A2. And so by comparing these, you can prove to yourself that the velocity here, if A1 goes to infinity, big tank, then V1 has to be 0 to compensate for that. So we can use conservation of mass to do that constraint, and we can use it to get this standard result, which is square root 2gh, which actually, if you have a mass that's sitting on a slope and a failing slope, the velocity at which that slope travels can be defined as the height that it drops on the rock slope, gravity, and this. We didn't say anything about the fact that this jet is directed downstream. The jet could equally be directed in this direction here, flowing with velocity here. And the velocity at point 2 in this direction would be identical to this because it'd be a streamline that turned the corner and went to your left. So there's nothing that we've said here that says it has to be pointed downwards. It's whatever the direction the jet is directed to. And so if it went out horizontally, it would go in an arc, right? It would fall down because it has gravity acting on it, but it also has horizontal velocity. And so it'd be like the guy peeing in Brussels, goes horizontally and then drops due to gravity. And you could calculate how far it goes from that. And we'll do that as a course of this. And that's it. That's it. Good. So good seeing you again. We'll get together on Wednesday and Friday. Give me any questions about tests. Yes?
There's a quiz for today's lecture. Is that another extra credit one?
Yeah, I was not going to be here. The funny story is that I was trying to get to China last week, and the visa I had meant that I didn't make it across the border. I got to Beijing, but I got to Beijing airport only, so I was supposed to be in flight today, and class was supposed to be online, but I didn't. I got sent back. And when they send you back, they don't let you drink on the plane. So 36 hours to get there, 8 hours to sit at immigration in Beijing, 36 hours to come back, no alcohol. get your passport given to you when you get off at Philly, drive for 3 hours to get home, and then wait an hour, and then give my presentation for my meeting online from my house, just in the nick of time. So I was happy that I could travel for 80 hours and still be, at my age, live enough to do something like give a presentation online. So I gave one on Friday night as well. So I had two meetings to go to. So that's my story. Yeah, do the quiz. Get the points. Yeah, thanks for the question. There you go. There's a story for you.